Okay, guys, bottom of this page, we were doing some looking at calculations. And we did what bonds are broken, what bonds are formed. We can get the values in tables. We'll practice that on the front page. There'll be other, there was one to do on the next page. We got 150, 170, that's a difference of 20. The bond strengths equate to your enthalpy, your delta H. Okay, the difference is 20. Is it plus 20 or minus 20 though? What's the final answer? Okay, you can find a formula, but let me tell you how you assess this. Which side is more stable? All the other bonds are the same. 170 means these are more stable bonds because these are bond strengths. The stronger the bond, the higher the number. Okay, that's the bond strength is the amount of energy it takes to break the bond. If it takes more energy, that means the bond is stronger. Right? So 170 means these bonds are stronger. We made stronger bonds than we broke. So the system has become stronger. Well, stronger should equate with higher energy or lower energy. Stronger bonds, are they higher energy or lower energy?
Higher energy.
No. Stronger bonds are lower energy. Okay? High energy bonds are weak. That's what we have to, okay? So these are stronger bonds. We get that from the number. Since they're stronger, they're more stable. In terms of energy, is this higher energy or lower energy? Lower in energy. The system has become lower in energy. Shows should the 20 be plus or minus. Has the system gained energy or lost energy going here? It's lost energy. Delta H is minus 20. Okay? Minus 20 kcal per mole. That's delta H. Question? Not a question.
So do we know like Hess's law that we learned from Chem, products minus reactants? Because we're focusing on bond strength specifically.
Products minus reactants. Well, 170 minus 150 would give you plus 20. I don't know what you're referring to, products minus reactants. Now, if you want an equation, I think it's reactants minus products. Wouldn't that give you minus 20? Wouldn't it? Okay. I would rather give you an explanation of why it's minus 20 and not positive 20. Okay. Where are we? How's this thing? Here we go. It's minus 20 kcal per mole. Thus we call it exothermic. The reaction gives off heat. Okay? Now heat is a general term. It gives off energy. It gives off, I reckon you can boil it down maybe to heat. But heat is a general term. Energy. The reaction is thus favorable. The reaction is usually described as going to be spontaneous, favorable, based on your delta H. Okay? So based on delta H, that reaction is favorable. We'll go back to it. What about entropy? Is that reaction favored by entropy? Two molecules going to one. Is that favored by entropy?
No.
So it's not favored by entropy, but it is favored by enthalpy. What's the overall? Which is delta G. Well, you have to say, well, which one is more important, entropy or enthalpy? I'm not so sure. Well, we can't answer as far as I know. Can't answer. Okay? And we're not going to be assessing the overall delta G. We're going to be assessing each individual. In this reaction, they conflict. Let me ask you this. If you wanted to make this reaction go to the right, well, first off, the energetics favor that. Enthalpy favors that. Let me ask you this. That still doesn't get it rate though, because just because it will happen doesn't tell us how fast it will happen. Let me ask you this. If this reaction was a little slow, would you want to heat it?
Yes.
Would you want to heat this reaction to drive it to the right? Why are you saying yes?
Because you got to overcome the activation energy.
No, because you drive it left, because you're pretty.
Okay, I can see where you could say, we could have conflicting views. Not necessarily.
Well, if it's giving off energy, it should be fluid.
It's exothermic, it's right?
So are you saying that any reaction can be driven by heating?
No.
Which ones cannot be?
An endergonic reaction might not get enough heat to be driven that way. Your delta H here is minus, so it's spontaneous in the sense that it wants to go to the right. But you may have some activation energy that needs to be overcome in order to get it to drive it to the right if the rate of the reaction is slow.
I'd have to think about that, but I'm thinking that I wouldn't want to heat this reaction, mainly because entropy. Is this favored by entropy? No. So entropy is a bad term. Temperature magnifies entropy, right? Okay, so you want to magnify the bad term? No. That's sort of my argument. I'd be careful about heating this, wanting to just automatically say you want to heat this. Yes, you do need to overcome activation energy. But once you're doing that, I would sort of want to back off and not heat it more. I know there's probably some argument. We really need to maybe compare it to another reaction and see. But remember, temperature magnifies entropy, right? Delta H minus T delta S. What does that mean to you? What does it mean to you in Gen Chem? Do you just heat every reaction? Okay. Let's move ahead. Okay, there's some discussion there. We may or may not have mentioned it. Another example here. Calculation. What did you get for this calculation here? Exothermic or endothermic? Anybody do this one? Anybody do this one? Okay, I know we have a test. So that's okay. But otherwise, I would want you got to look ahead. You got to do problems in here. You got to be prepared for class. Look ahead. Many of the handouts are going to have things to do or questions that are being posed, etc. Let's do this one real quick. What bonds are broken?
CH and 3CC.
That CH is no longer there because now it's CF. What type of carbon is this? Primary, secondary?
Tertiary.
Okay, so we got a tertiary, let's see, a carbon, which is tertiary CH. That's broken. How much is that worth? Where's the front? Is there a tertiary CH in the table in the front? Yes, 97 kcal per mole, right? Is that right?
Mm-hmm.
Everybody see that? Table in the front, is it 97?
Mm-hmm.
Okay, what else is broken over here?
FF.
FF bond is broken, what's that? 38? What is this, 135? Okay, this is kcal per mole, 135. What's formed?
CF.
A CF, that is tertiary, but it may or may not distinguish between carbons in the table. What does it give us? I only see one CF bond, and it's 115. Now, that's all we have. So from this table, we're going to have to just go with that number there. And that is a, well, methyl is not even primary. But that's the only CF bond there. Okay. Now, hopefully on a quiz or a test, there will be something that's very clear to which one you choose. Okay. So in this example, we're just going to have to go with that. It was 115, right? And what else did we make over here?
HF.
We made an HF bond. What is that worth? Where's HF at?
Top right.
Okay, middle right, HF 136. This adds up to, what's that, 11? 251? Okay. First off, what's the difference in the numbers?
Over 100.
What's that, 65, 66, another 50? What's that,
116, right?
116?
Yeah.
Okay, 116 is your difference. Is it plus or minus?
Plus.
Okay, well look which side's more stable? The side that has the 135 bonds or the side that has the 251 bonds?
251.
Which side's more stable? This side, stronger bonds, more stable. Okay, since it's more stable, is it higher energy now or lower energy now? It's now lower in energy. By how much? This. We say the system, when it came over here, it lost energy. Delta H equals that. Okay, what were the units here? Kcal per mole. Okay, if you do a mole of each of this, we won't get into stoichiometry there. Where did this heat go? That plus heat. Heat was produced.
So in this case, we should be able to heat it, right?
No.
No.
No,
It's gonna give you heat anyway.
Because we got heat on the other side, yeah, sorry.
I reckon you could argue that if you heat it, it's just going to come this
Yeah,
way.
yeah.
I think all those arguments are sort of up to, well, is there anything else?
Well, so,
Anything else going on? In terms of entropy, two molecules going to two, so entropy is not really bad or good, unless you look at entropy more closely than what we're doing. In the end, delta H is that. The reaction is exothermic. There you go. Reaction's exothermic. Is it favored or disfavored? Well, that's sort of a general term. It's favored. Exothermic reaction is favored. They're known to be they're said to be spontaneous. Now, does that mean this reaction is actually going to take place at a given temperature?
not at a meaningful speed.
Well, we do have to overcome the activation energy, and then we're getting into rates. Okay? So there's deeper discussions for right now. This reaction is described as exothermic. Delta H is negative 116. We did a little comparison. Repeat this using iodine instead of F2. Okay? I want you to do that on your own. Do that same reaction there, but use I2. Look at the difference. And then try to answer why the difference in the two. Why, you're going to see a big difference. Okay? Please also answer the questions on the front. Which reaction gives off the most heat or energy? Could you now do that? Two reactions. Okay? I give you some bond strengths there because they may not be in that table. Which reaction is endothermic? Okay? Based on your calculations, you can then, okay? Basically, please answer the iodine question and then go back and answer the questions on the front. We'll look at those tomorrow. Okay, kinetics. Of course, it describes the rate of the reaction. Depends on the activation energy. At this point, we need to introduce and be able to understand a reaction coordinate diagram. Hopefully you saw some of these in Gen Chem. Where we can plot the energy as it proceeds from reactants to products. This can be listed as free energy. It can also be listed as enthalpy. Basically, ultimately it's some type of energy. This is the progress of the reaction here. We start with reactants, we go to products. Reactants are going to have a certain energy. It really doesn't matter what the absolute value is. What matters is, well, how does the products compare? So the products in here, lower in energy. So ultimately, this reaction is exothermic. Okay? Now, they're given a delta G. I would probably call that delta H. For us, it really doesn't matter too much. Very general. Does the energy profile just go boom right to this level? No, it actually is going to rise first. And you got sort of a mountain and then you fall down. As it rises, now this is a one-step reaction here that's shown. What is this energy right here?
Activation.
And you can call it, you can maybe show here. This here is the what? That's the activation energy. That's the energy barrier that must be overcome to do the reaction. Okay? So even though the reaction may give off heat, give off energy, you have to put energy in from the start point to get there. This is reactants, this is products. What is the species that's right here? I mean, do you call that reactant? Do you call it product? What do you call that sits right there?
Unstable transitional species.
Transition state?
Yeah.
Yeah, that's some type of transition state. That's the, maybe call it an activated complex. This is where like the bonds are breaking and forming. It's like Bionic Man. The bond's forming. As the bond's forming, the other bond may be breaking. It's that process. That's sort of a higher energy process. Transition state, activated complex. But you have to supply enough energy to get to that activated complex. Then you can start falling back downhill. What is this? Bonds breaking, but barely breaking, barely breaking. Oh, they're really breaking now. They're like, it's the maximum energy point. Understand what that means. Activation energy, exothermic. Where this over here, this reaction looks like it's not exothermic, but endothermic. Okay? Let's look at these four down here. We can ask a couple of questions. Which reaction of these four is most favorable? Favorable is sort of that generic term like spontaneous, which, you know, favorable to me is a thermodynamic term based on your delta H. Okay? Exothermic reactions are going to be favorable, endothermic reactions not so favorable. Doesn't mean you can't do them. Which one of these looks like it's most favorable?
B.
Well, that's endothermic. Both of these are endothermic, right?
I say A.
Okay, I wish you could see the difference here, but
Smaller than that.
that's actually a greater distance. Okay. I would say B is most favorable, but what does that really mean, say most favorable? Does everybody agree that was most favorable? Most exothermic.
But since, maybe this is a dumb question, but since it has a lower activation energy, would it be more likely to happen?
Activation energy
More
doesn't change the
spontaneous. A is more
speed of
spontaneous.
just
Do
a
what?
lowest activation.
Say A is more
I guess,
spontaneous.
can you give like a specific definition for favorable?
No, I can't.
So, because like I see that one's more stable, but on this one it's gonna happen, it's gonna be more likely to happen at, you know, like room temperature or something. That's why I'm trying to wrap my head around, like, where do we draw the line for favorable?
It's spontaneous.
I call them both, they're both favorable. Maybe I don't understand the terms favorable and spontaneous. To me, I've always thought it's based on this delta H. I do see this as a lower transition state, and if we ask this question, which favorable reaction is fastest? A. Because, well, to me, favorable is a thermodynamic term, fastest is a kinetic term. Clearly, fast means rate, kinetics. And what is that based on?
Activation energy.
Activation energy. Yeah. The getting over this hump is going to be easier than getting over this hump. So at a given temperature, there will be enough energy supplied to form the transition state compared to this one.
So like basically at some temperature, B would kind of be more favorable, but at like a lower temperature, would it be A?
It depends on the conditions of the system.
Whether it's reversible. Yeah. Ultimately, we're not getting into this that deep. And I do agree that maybe my favorable is not, I'm just basing it solely on delta H. If you base it solely on delta H, this one's most favorable. Which one's fastest? Well, this one, because importantly, lower transition state energy, lower activation energy is going to make it fastest. It's ultimately like this. If you react a diamond with oxygen and you do a calculation, you will see that it's highly exothermic. So you'll have diamond, and then you'll have over here CO2 and all the products, water. Okay? Diamond plus oxygen. So this would be called favorable or spontaneous. Does that mean that your diamond explodes? It reacts with oxygen? No, if you have a diamond, you know it does not do that. Okay? That's because this is so high that you never get over that at a reasonable rate, and the rate is basically nil. Okay? That's your rate there. This is delta H. Okay, let's look below. Below is an example of a two-step reaction. Most reactions are multiple steps, multiple elementary steps. This would be a two-step, where we form some intermediate, one intermediate here, and this is a carbocation intermediate. And it follows this energy well. Okay? But we start here, we have an activation energy, okay, E sub A, leading to this. Okay? But this is a discrete intermediate. It's not like the transition state where bonds are breaking, bonds are forming, which is higher energy. Okay? That's your transition state, leading to this. This is an energy well. Comes down here and sits in this well. And from there, it can move on, and this can convert and form a final product. But that's going to have an activation energy too. Okay? Get here. So you have two activation energies. Now, we can say up to two steps, which is the rate determining step.
First one.
Okay, I hesitate doing this, but I'm going to do that there. Which one has the highest activation energy? Obviously the first one. First one's going to be your difficult step. It's going to be called the rate determining step. Okay? Because you may have enough energy to do this, but if you can't do that, then that's going to control the rate. It's like a bottleneck. If you're emptying water out of a Coke bottle, getting to that end is not the rate determining step, it's getting out that little end. Okay? You guys rushing to get out that door, you rushing all over there is not the rate determining step. It's probably going to be getting out that small door. That's going to be the rate determining step. So I don't want to speed you up getting over there. What I want to speed up, if I want to change the whole process, is to speed you up getting out that door. Okay? If we want to increase the rate of this reaction, do we need to make this faster?
No, we're gonna make
No, we need to make this faster, and thus we need to lower this. If we can lower this, it'll make that faster. How might we lower this?
catalyst.
Yeah. Yeah.
Or increase the temperature.
That's not the answer.
Okay.
Everything. Okay, those are questions, and we'll do some of that. So rate determining step, number of transition states shown there.
Two transitions.
Yeah, we've got a transition state leading to this, and then a transition state, okay, leading to that. Okay, let's look on the back. How can we make a step faster? This is two sort of first elementary steps to lead to some intermediate. This is showing where we actually may start at the same spot. Both of these here. Okay. So this is supposed to be the same reactant. Envision this the same reactant. And the reaction can form two intermediates, two possible intermediates. It can either form this cation or this one. Okay? Now, as we'll learn, it actually was on the test, which cation is most stable?
Tertiary, the bottom one.
This one is most stable because it has 3 carbons inductively donating, where this only has really 1 chain. So this is more stable. Since it's more stable, don't we show it at a lower energy point?
Yes. Exactly.
Okay? Now, here's the thing we're going to always sort of say. The transition state leading to a lower energy intermediate is itself going to be lower. Now that's going to be sort of a starting statement. We will have exceptions to that. Okay, but for us, a lower energy intermediate is going to have a lower energy transition state or activation energy. You see how it is? So this thing has a choice. It can either go that pathway or it can go the higher energy pathway. Which pathway is it going to prefer?
The bottom.
It's going to prefer the lower energy pathway, and thus it's going to come here. That's why when this particular reaction takes place, this cation is going to form. Now most of you will want to say, well, it's going to form because it's most stable. That's not really why it forms primarily. The reason why it forms is because the activation energy is lower. But since we're saying because it's lower, that's lower, I understand what you're getting at. Okay. Now here's an exception. Look at this reaction coordinate diagram. Here we start with a reactant, and it gets a common intermediate. So it's just one intermediate, but from there, it can then go 2 different ways. From there, you can get what's called a 1,4 product or a 1,2 product. Don't worry about that. The important thing here is the 1,4 is lower in energy. You see how it's lower in energy? Now, based on the opening statement I just said, we would say lower in energy means the activation energy should be lower. Right? Well, this right here is a case where it's not. So This already is an exception to my statement. So, which way is this one going to go? We get here, from here, where is it going to go? Is it going to go that pathway or that pathway?
Bottom.
It's going to go the lowest energy pathway. It's going to be preferred. If water's going down the road and it can go up this hill or maybe over here, which way is it going to go? It's going to go down the hill. Assuming it's not a hurricane. If you have a hurricane, you may get some going up the hill too, right? Okay, let's go prefer this. What does this lead to? It actually leads to the highest energy, higher energy product. So that's an exception to what I already said before. Ultimately, there are exceptions to that statement. This is just some examples of reaction coordinate diagrams. We understand that if you went here, that would be a two-step process where we first formed an intermediate with a transition state. Then we went a second step to get the final product. Of the two here, to get either one of these, which is the rate determining step?
First
Left.
left.
Oh, sure. First step.
Okay, it's a rate determining step from either one. First step is the rate determining step. One intermediate as well. Basically becoming familiar with the sort of the topography of a reaction coordinate diagram.
So if you want the 1,4 product, would you heat it after the intermediate or during the intermediate step quickly? Or how would you go about that?
How would you force it
We'll actually look at this later during test 3. If you heat it, it's not going to make it. It's still going to prefer this. Okay. The answer is you have to establish an equilibrium. If you can establish an equilibrium, then thermodynamics takes over and it'll prefer the 1,4 product.
I agree with the physics now.
Okay? Because an equilibrium implies reversibility. And once you can go back and forth, then the thermodynamics becomes more important. Okay, the one on the bottom. How many intermediates in the one in the bottom? How many intermediates in this reaction mechanism or overall reaction process? You see any intermediates? Starting materials, products? There's no intermediate because there's no intermediate energy well. There's just one what? What do you want to call this here? One transition state where like A is forming to B and the BC bond is breaking. It's just one transition state. Okay? Later on we'll do like an SN2 mechanism and it'll have one transition state and it'll look like that. Basically all this is sort of intro. Okay? Really, I could have just introduced that stuff when we get to it. We're going to see all this again, but I just kind of fly through it real quick. Okay. You need to be looking at the reaction coordinate diagrams. I think the Klein book has a chapter on just thermodynamics, kinetics, reaction coordinate. Questions about those? Please do the calculations. I'll try to figure out what favorable means. Okay. Have another handout. We'll split it in half. While that's coming around, I'll just remind you about here. We looked at this already. Okay, we're going to look at reactions, alkene reactions. Alkene has a pi bond, and because that pi bond is not held as tightly as a sigma bond, those electrons are sort of available to go react. It's like the electrons of a base. We're not going to call these electrons a base, but they act similar to that. They're available to go react. We looked at the front. Remind you of the back. We have outline. And the first thing that we will look at is reacting an alkene with HX to make what? You do need to know the names of the products. Terminology. When you react with an HX, what do you form? Alkyl halide. Not only do you need to know that, but knowing that then helps you predict what you get. Okay? Know what you're doing, terminology. Okay? There's our outline. What I'm passing you around right now is our sort of written notes that we're going to be working with. Everybody got the handout? Okay. Here we go, guys. Y'all ready for this? All right. We're getting into the hardcore, what organic is about here, okay? Reactions. All right. If you don't jump on it, if you get behind, it's going to be hard to catch up. If you work hard, put in the time, as we move ahead and into organic 2, it will come easier and easier. Okay? Outset's very important. Okay, addition of HX to alkenes. We also have on the yellow, the second page of the yellow is our sort of written outline. A, electrophilic additions to carbocation intermediate. That should tell us a lot. What type of intermediate are we making? Carbocation. And so I have text here that's supposed to be very informative. Don't read the text. Okay. Double negative. Please read the text. Roman numeral 1, what are we doing? Addition of HX to alkenes to give alkyl halides. What's another term that can describe that? Hydrohalogenation, because we're adding a H and a halogen. Hydrohalogenation. So that's that outline we'll be going by, and here it is on the white sheet. Here it is. All right, I'm not going to have a Roman numeral 1 like the yellow page, but it's there. All right, here's an example of reaction. You take this alkene, certain formula, react it with HBr, which is, HX. HX can be HCl, HBr, or HI, typically not F. A lot of reactions don't work that well with fluorine because fluorine is stubborn or very hazardous in some cases. Okay? HBr, we get this product. First off, there's only about 5 or 6 types of reactions in chemistry. Additions, eliminations, decompositions, which is elimination, substitutions. What is this reaction in the broad classification? These two are adding together to give that. The HBr is said to be adding to the alkene. Okay? It's like an addition, like 4 plus 2 is 6. It's coming together. We're not replacing anything. Nothing is being replaced here. Okay? Yeah, we are breaking bond. It's an addition reaction. That's why it's called an addition. And in fact, the biggest heading up here is electrophilic addition reaction. That's chapter 9. All these reactions will be additions. Classification, organizing your thoughts, terminology, it's all there to be organization. See what we're doing. Always make sure you see what we're doing. Here we go. What's the mechanism for this? Mechanism will be done for all reactions. Okay. First off, the HBr is polarized. Okay? When we did acid-base, same thing. The H is sort of a partial plus. Okay? Things that are negative can attack this, like the base could attack this. All right? Now, you can show this either covalent or ionized. Either way will work in your mechanism. I like to do it both here. Moving forward, we'll do it different ways. Alkene. Well, first off, I don't see a lone pair. Before we had like a base, the lone pair attacking the H.
Yeah.
There's no lone pair. Instead, we have a bonding pair. The two electrons in the pi bond are available to go react. Now, I rarely do this, and most folks rarely do it. Oh, I'm sorry. First, let me show you this. Here's the reactivity. These two electrons are said to move and go make bond to H. Okay? And when they make bond to H, we kick off the bromine, just like an acid-base mechanism. And what does this arrow mean to you? Electrons move on to bromine, and we get four lone pairs, and we make Br minus. So that should be the easier point. Well, what's going on here? The two electrons in the pi bond are said to break away from this carbon. They're going to swing over here and go make bond to that H. Okay? So this is sort of pulling and like this. Boom. Go and make bond to H. All right? And when this goes and makes bond to H, we now have that bond to H. A lot of times I'll sort of highlight bonds we just made by drawing a zig line on it. But the electrons moved away from this carbon, so it only has 3 bonds now. Since it only has 3 bonds, what's the charge of that carbon? Positive. So we created a positive carbon. What do we call that? Carbocation. Okay? And since we're under Roman numeral A, all these reactions are going to have what type of intermediate? Carbocation intermediate. There it is. Plus that. An intermediate. How do we get final product? The minus then bonds to the plus. These electrons, remember every time you do a mechanism arrow, you start by saying what?
These electrons.
These electrons do what? Make bond to the carbon, minus attracted to the plus. Make bond. When that makes bond, what do you have? You have that product there. Okay? Importantly though, what's new on this N carbon?
One more H.
There's an extra H there because that's a CH3. Where, how many H's are on this carbon?
2.
Okay? Aren't there 2 H's there?
Yeah.
And now this is a CH3. No matter how I do it, I'm going to want to do it another way, but I'll draw them all 3. There's an extra H on that N carbon. We have added HBr to the molecule. It said that terminology is we've added HBr across the pi bond. Sort of, that means to each carbon. So this is addition of HBr across the pi bond to give an alkyl halide. You can do this with HCl or HI. Here's your mechanism. You can also do this by first ionizing the HBr. Okay? You can either just show it ionized. If you want to get to that point, starting from covalent, you just say, hey, this is just going to ionize. What does this arrow movement give? I mean, doesn't that just give Br minus and the H is sitting there with nothing?
Yeah.
So it's plus. You could first do that. I'll allow you to just show it ionized if you want. But you do need to know this, what's going on here. Where this is a mechanism arrow, where this is sort of the reaction line, like this leads to this. Question?
Why does the hydrogen preferentially go to the tertiary carbon as opposed to the primary carbon?
Very good. We have to answer that. That's a critical question. We'll get to that below. Question?
It's actually a very the same thing, but just so I know if I'm thinking wrong, bromine's so electronegative that he's basically not sharing. Is that kind of why that's happening? Because I was trying to understand why it happened.
Kind of what happened?
Like, because because the like bromine's really not sharing. Is that so? It's basically ionized to begin with, and then you've got a pi orbital sitting there and a hydrogen sitting there that's positive, and then they interact. Because he's so electronegative, he's basically hogging the electrons.
Why does this ionize?
No, why does it react? It's the same question in a different way.
So why isn't it the tertiary?
Yeah.
Just 'cause.
We haven't got there yet. I thought you were saying, why does this ionize?
No, I know.
It only ionizes when you put it in the presence of a base, like
Right.
water. But, I mean, you could show this ionized because we know it tends to be ionized. Okay, lots of questions to address. We'll move forward. One thing I want to show you before we move down is, what you'll never see here is, what you could do before you do anything is, you could polarize the pi bond. Okay, draw that fresh. There. We polarize the pi bond by moving these electrons here. What does that arrow movement give? I'm moving the pi bond, and I'm moving them onto this carbon as a lone pair. So that becomes this. Now what's the charge? Well, there's two H's there, so that's a minus. So what's this?
Plus.
Okay, that's a polarized resonance structure where all we moved is pi electrons. Now at this point, you could use this form of the alkene, and you could say, hey, this is going to act like a base, and come in here and attack the H and kick off that. And what does this give? Well, it gives the same thing. It gives that. Okay? Because this would now be binding to an H, as we showed, and we'd be left with the cation. So if you want, you can think about this being first polarized. But then the question is, why did you polarize it this way? We'll get to that. Now, no book is going to first polarize this because this is really not that polarized of a pi bond because they're both carbons. But this could help you mechanistically if you see how this looks familiar to what we've done before. Okay, reaction coordinate diagram. Can we draw one for this reaction? Let's try to finish up right here. Okay, we do something like this. This is reaction progress, right? This is some type of energy. I'll just say E, right? This is going this way, this is going this way. We start some arbitrary level. We start with what?
Reaction.
Alkene. That's the energy of the alkene. We're making an alkyl halide. Do you want to put that higher or lower than this? You can pull your calculator out, do some calculations. But I want to put it lower. Anybody tell me why I'm thinking lower? Look what we did in the reaction. We broke a pi bond, and we made two sigma bonds. So two sigma bonds more stable, thus lower in energy. Okay? So I guarantee you if you do calculations here, it will be exothermic. So I'm going to draw this down here. This is your what? Alkyl halide product. How many intermediates in this reaction? One. Where do you want to put it compared to these? Here's the important thing. It's charged. Since it's charged, it's going to be higher in energy. We're going to put it kind of up here. Now, if we do sort of the pathway, what's it going to look like? Straight there or an activation energy? We'll do an activation energy. Fall into this well. Now, let's end here. Okay, guys? Is it going to go straight there or an activation energy?
Activation.
Activation. Is it going to be a tall activation energy or not so tall?
Not so.
It's not going to be that tall. Just a wee bit coming off of this area here. Why? Because we're falling way downhill. Does it take much activation energy to fall downhill? No. Go to the top of the stairs and just sort of bend your knees and lean forward. You're going to go. Okay? Doesn't take much to fall down. Okay. We're out of time, guys. If you need to run, please take off. Questions, though, if you're...
Those are both ionic species. Why would there be any activation energy at all? Wouldn't that be just spontaneous?
This is your carbocation.
Right, but the second hump, that reaction, wouldn't that have zero activation energy? Since they're both ions, wouldn't they just grab each other?
It's going to be very negligible. I
Yeah,
think it's usually shown as some. Okay, guys, lots of reading to get up to this point. We're moving ahead. Thank
I'll be the one that he'll be like, you can look at this. I think about what's happening. Nope. I have your. Yep.